This one here is C11H15ON, and that would be 5 double bond equivalents. We have an aromatic ring here, C6H5. It's in the 7 to 8 aromatic region. We've got 2 CH2 groups, and we've got a 6H here, that's going to be 2 CH3s. Now when deciding whether a 6H is going to be 2 CH3s or 3 CH2s, we can look at a number of peaks. And what we usually find is that when there's 1, 2 or 3 peaks, that generally indicates that we have 2 CH3s. And then when we've got 4 peaks, that generally indicates 3 CH2s. Now all of this is demanded by symmetry, and if you'd like you can stop the video, you can read my discussion about those symmetry requirements. The pieces left over, we've got a C, an O, a double bond equivalent, and an N. Since we don't have any C double bond N groups here, we're going to go with the C double bond O. And then we have left over here just one nitrogen. And that nitrogen doesn't have any hydrogens on it because there's no H's left over, so we're just looking at an N. Now that should be the correct pieces, and we can go ahead and put everything together. Now a couple of things we can see, we've got 2 CH2 groups, they both have 3 peaks. This indicates that they're probably next to each other. The reason I say that is because the CH2 here would have 3 peaks, which means it's next to 2 adjacent hydrogens, and this one here has 3 peaks, so it's next to 2 adjacent hydrogens as well. So we have a CH2 next to a CH2. Further, I know that CH3 is not connected to either side of this grouping, because otherwise this CH2 would appear as 6 peaks, for example, because it have 5 adjacent hydrogens, including the CH3. So I know that these two are together, but they are put apart, probably by the C double bond O and the N. They're definitely involved on either side here to keep this apart from the CH3. The other interesting peak here is the 6H for 2 CH3 groups. Now you'll notice it's a single peak, which means that both the CH3s are equivalent and that they are next to something that doesn't have any hydrogens on it. The best way that I can put that together then is to go ahead and put the CH3s on the nitrogen like I have here. Now the C double bond O needs to be put somewhere in the structure as well. So I'm liking what I'm seeing here. One other clue that I can get here is from the splitting in the aromatic region. What we notice is that when a C double bond O group is attached to an aromatic ring, it tends to split the ring into 2 peaks, and they're centered usually a little bit over 7.5 ppm. And if we have an oxygen or something equally activating on the ring, it tends to split the ring in 2 and center it around 7 ppm. And an alkyl group will just generally leave it as a single peak. Now what we've got here is a double set of peaks, or two sets of peaks. They do seem to be centered around 7.5 ppm. That would indicate that we do have a C double bond O directly attached to the aromatic ring, and that this should end up being our structure.